In our last video, we talked about how we can count in other bases, and we compared counting in other bases to counting in decimal. And so in a way you can use that when you're looking at some really small cases, like if you wanted to say, figure out what 12 in decimal is in a different base, you can sort of just look at the table and build your way up. But if you're looking at a really large decimal number and you want to know what is it equal to or how would you express it in another base, building up that counting table all the way up is not really an effective way to do that. Okay, but luckily we actually have a couple of different methods we can use to try to express a decimal number. Remember, decimal is our normal number system. This is just the number 192 that we're used to in another base. So let's start by trying to convert the decimal number 192 into ternary, right? Remember, ternary means base 3. So this is only going to be using digits 0, 1, and 2, right? Using those 3 digits, 0, 1, and 2. We have 2 different methods of doing it. The first one is to really just try and express 192 as a bunch of powers of 3 added together. Because remember, that's really what it means to express something in ternary. It means to write it as a bunch of powers of 3. So what we're going to do is we're going to subtract the nearest power of 3 from 192, and we'll just keep repeatedly subtracting until we get down to 0. Alright, well, what are the nearest powers of 3 that we have to use here? Alright, let's keep in mind 3 to the 0 is equal to 1, 3 to the 1 is equal to 3, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, 3 to the 5th would be, it'd be 81 times 3, so 243. Oh, that's too high. Right, if I were to subtract 243 from 192, I'm going to be negative, so forget about this. Right, the closest power of 3 to 192 would be the number 81. So I start here, 192, and I subtract 81. What am I left with? Well, 1, just 11. Okay? Oh, no, sorry. 111. All right, I'm going to repeat this now. I'm going to take my new number, 111, and I'm going to subtract the nearest power of 3. It's still 81, so subtract 81 again. We get 0, 3. So we get 30. All right, now what's my nearest power of 3 to 30? Well, that would be 27. So subtract 27. I'm left with 3. Now I subtract the nearest power of 3. That's just going to be 3 to the 1. And then I get to 0. All right. What this means is I can sort of pick out 3, 27, 81, 81. I can pick out those digits here, and I can say that this number 192 can be expressed as 81 plus 81 plus 27 plus 3. And in particular, I can express these as powers of 3. So I have 2 copies of 81, which is 3 to the 4th power. Then I have 1 copy of 27, which is 3 to the 3rd power. I didn't subtract any copies of 9 here, right? So I can say that I have 0 copies of 3 squared. Then I had 1 copy of 3, 3 to the 1 power. And I didn't have to subtract any 1s at the end. I didn't have to subtract 3 to the 0 at all. So I didn't have any copies of 3 to the 0. And if you're wondering why am I putting in these zeros here, they're sort of like placeholders. The same way that sometimes a decimal number has a 0 in the middle of it, it's a placeholder, and we need that there so that we can differentiate between this number, right? And if I didn't have these, then just picking out these coefficients 2, 1, and 1 is going to give you a different ternary number that's not going to be equal to 192 in base 10. All right. So essentially this is what I'm doing though. Now that I've written it as a sum of powers of 3s, I'm just picking out the coefficients here, and those are going to be the numbers in my string. 2, 1, 0, 1, 0 in ternary. And I should be clear, this is 192 in decimal. So 192 in decimal is equal to 21010 in ternary. And notice, inside here, all of your digits, 2, 1, 0, 1, and 0, those are all digits that are less than 3, because we should only be using those digits when we're expressing something in ternary in base 3. All right, so that's one way to do it. Now there's actually another way that you can use if you want to convert from from decimal into a different base, and that's using repeated division by your new base. So our new base is 3. So another way that we could have done this is using repeated division by 3. So start with your decimal number 192, divide by 3, and see what happens here. So when I divide 192 by 3, I'll get, let's see, 18, bring down the 1, 3 goes into 12, 4 times, and I don't have any remainders here. I have a remainder of 0, right? The remainders is going to end up being what's important, so I'm just going to keep track of my remainders each time. All right, now I take my new number, 64, and I'm going to divide that by 3. How many times does 3 go into 64? Well, 3 goes into 6 twice. 6 minus 6 is 0. Bring down the 4. 3 goes into 4 once. 1 times 3 is 3. And I've run out of numbers here, which means I have 21 with a remainder of 1. Okay, here's my new number, 21. I'm going to divide again. So 21, we divide it by 3, we get 7. 7 times 3 is 21. And I have a remainder of 0. All right, my new number is 7. Almost out of space here, but luckily I'm getting close to 0. I'm going to divide 3 into 7. 3 goes into 7 2 times with a remainder of 1. Finally, I take this 2 and I divide. How many times does 3 go into 2? Well, it goes in 0 times with a remainder of 2. All right, I can't divide anymore. I've already gotten down to 0. It doesn't make sense to do any more division. So now, to turn this into a ternary string, I'm essentially just picking out the remainders and reading it backwards. Right, so if I read these backwards, I'll have 2, 1, 0, 1, 0. So 2, 1, 0, and 0 in ternary is equal to that 192 in decimal. We got the same answer that we got up above. We just did it using 2 different methods. All right, so it sort of makes sense. These seem like they're pretty different methods, but remember that repeated subtraction is pretty much just the same as division. That's what division is, it's repeated subtraction. So we're doing kind of the same thing here, but we're just sort of approaching it in 2 different ways. If you are not comfortable with long division, well, don't use this method, right? Don't use method 2. It's easy to make a mistake if you haven't used long division in a while. If you're bad at subtraction, don't do this. And if you're bad at subtraction and division, well, what the heck are you doing in this class? No, I'm just kidding. Right, use whichever method you're more comfortable with. We'll do one more example. So let's say we want to turn the number 3462 in decimal into base 5. All right, I don't really know if there's a special word for base 5. I just wrote 5. But what I mean here is the digits would be 0, 1, 2, 3, and 4. Right, you have these 5 distinct digits. And so the 2 methods here would be repeated subtraction of the nearest power of 5. All right, so let's go ahead and write our first few powers of 5. 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. 5 to the 4th is 625. 5 to the 5th, oh, I have to do scratch work again because I forgot my scratch work page downstairs. So this would be 625 times 5. 3125. And I can see how if I multiplied by another factor of 5 here, I'm going to get something way, way bigger than 3462. So I don't have to go any further than this. This is going to be my nearest power of 5. So this method says to subtract our original number, 3462. Subtract from that the nearest power of 5, that would be 3125. Okay, what do we get? Let's see, so we get 7, we get a 3, and a 3, so we get 337. All right, what's my nearest power of 5 to 337? Well, this 5 to the 5 is too big, 5 to the 4 is too big, so 125 would be the next one. So we subtract 125. What do we get? We get 212. All right, what's the nearest power of 5? It's going to be 125 again. So So subtract 125 again. We'd get, let's see, 87. All right, so what's the nearest power 5 to that? 125 is too big, so I'm going to subtract 25. We'll get 62. Again, nearest power 5 is 25, so subtract 25 again. We'd get 37. Okay, subtract 25 again. We're getting closer. We'll get 12. My nearest power 5 to that, 25 is too big, so I'll subtract 5. That gets me to 7. Running out of space here. 7 minus another 5 gets me down to 2. So what's my nearest power of 5 to 2? I guess it would be 5 to the 0 power, right? So I'd have to subtract 1 and then subtract 1 more time to get us down to 0. All right, now what do we have here? We have 1, 1, we have 5, 5, we have 3 copies of 25, 2 copies of 125, and 1 copy of 3125. So I can express this original number 3462 as 3125 plus 2 copies of 125 plus 3 copies of 25 plus 2 copies of 5 plus 2 copies of 1. All right, and now I just want to rewrite this as powers of 5, remember. So this is just 1 copy of 5 to the 5th power. We didn't have any copies of 625, but we still need that 0 placeholder. We have 0 copies of 5 to the 4th. Then we had 2 copies of 125, so that's 2 copies of 5 cubed. Then we had 3 copies of 5 squared. 2 copies of 5 to the 1, and 2 copies of 5 to the 0. So now I'm just pulling out those coefficients, right, to express this in base 5. It'll be 1, 0, 2, 3, 2, 2 in base 5. Right, so the number 3462 in decimal is equal to 102322 in base 5. And using the repeated division method, well, we'd start with that original number, right? Remember, we're trying to translate 3462 in base 5 into decimal. Oh, sorry. From decimal into base 5. Okay, so we're just going to divide over and over again by our new base 5. So how many times does 5 go into 3462? Let's see, this would be 6. So 46 goes in 9 times. Twice, 2 times 5 is 10, and we get a remainder of 2. Okay, now we'll do this again. We'll take our new number, 692, and divide it by 5. 5 3 times. Bring down the 2, 8 times, and we get a remainder of 2. Now take our new number 138 and divide it by 5 again. Make sure you can actually see this. Divide it by 5 again. Alright, so it goes in twice. 38, it's going to go in 7 times. We get a remainder of 3. Okay, now take our new number. I'm running out of space, so I'll just finish it up here. 27 divided by 5, it goes in 5 times with a remainder of 2. And how many times does 5 go into 2? Well, 0 times with a remainder of 2. And remember how this method works. We're doing, wait a minute. Where did I mess up here? 2 times 5 is 10. 7. Oh no, I've messed up somewhere. 2. Oh, ha ha ha. Oh, this was silly. I see where I messed up. All right, remember what you're supposed to do is take your new number, right? Divide 5 into that. How many times does 5 go into 5? Right, don't take the divider, right? How many times does 5 go into this number, 5? 1 time, with a remainder of 0. Then you can take this 1, your new number 1, and say how many times does 5 go into 1? All right, 0 times with a remainder of 1. There it is. All right, so we can pick out our remainders here. Remainder of 1, 0, 2, then 3, 2, and 2. Remember, we're reading these off backwards, so we have to read it like this. And it's going to give me 1, 0, 2, then 3, 2, 2. Oh boy, that was rough, guys. See, this is why I always use a subtraction method, because I'm not very good at division. 34, 62 in decimal. All right, see, another good reason for doing this is you can check your work. I got a different answer, and that's how I knew that I messed up in one of them. You don't always know which one you messed up in. That's the hard part. All right, but you can use either one of these methods. We're almost there, almost done here. The last thing that we want to do is talk about how to calculate in other bases. Right, so let's say you wanted to add or multiply in another base. For example, if we wanted to add 243 base 5 to 1402 in base 5. One way to do that would be to convert each one of these into decimal, add them together, and then take that result and convert it back into base 5. But that's a little annoying to do. You have to do 2 separate conversions there, and you have to remember which is which. Just a little bit harder. So as it turns out, you don't really need to convert to base 10 to do arithmetic. You just need to convert your entire addition table, the one that we're familiar with in base 10, convert that into base 5, and then use that to add these like we normally would. All right, so let's fill out this addition table. 0 plus anything is just going to be that original number back again, right? 0 plus 0 is 0, 0 plus 1 is 1, which means this first row is easy, and similarly, 0 plus 0, 0 plus 1, this is just going to give you the same thing back here. Now, remember, we're in base 5 here, which means the only digits we can use are 0, 1, 2, 3, and 4. If you get any higher than 4, you have to add a new place and go up to 10. So 1 plus 1 is just 2, that's fine. 1 plus 2 is 3, that's fine. 1 plus 3 is 4. 1 plus 5, 1 plus 4 would be 5, but we don't have a 5 to use here. So when you run out of digits, your next number up would be 1, 0. Right? This is saying 1 copy of 5 and 0 copies of 1 in decimal. All right, so this is how we would count in base 5. Similarly, I could actually this is symmetric, so I can just fill it in like this. All right, 2 plus 2 is 4, that's fine. 2 plus 3 would be 5, but we don't have a 5 to put, so we have to put a 10 here. And similarly, 2 plus 4 would be our 6, but we don't have a 6 digit to use, so that's like 5 plus 1, or the number 1, 1 in base 5. All right, I'm going to fill out my table because it's symmetric. 3 plus 3 would be 9. All right, what is 9? Well, 9 would be 1 copy of 5 plus 4 copies of 1, so this is like 14. Wait a minute, that's not right. 3 plus 3, oh, not multiplication, you ding-dong. Sorry. 3 plus 3, not times 3. 3 plus 3 is 6, right, which is 11 in base 5. And then 3 plus 4 would be 12. 3 plus 4 is 7, which is 12 in base 5. We pull this out. And finally, 4 plus 4 is 8, which is like 13 in base 5. All right, with this in mind, we can now use this to add vertically like we normally would. We're trying to add 1402 plus 243. So we line it up just like we do in our traditional decimal arithmetic and use the table to help us add vertically. So start with 2 plus 3. 2 plus 3 in the table tells us it's 10, right? It's 10 in base 5. So it's a 0, and then we need to carry the 1. So what's 1 plus 0 plus 4? Well, 1 plus 4 is 10 again, right? A 0 and carry the 1. Now we're adding 4 plus 1 plus 2, right? That's like adding 4 plus 3. So 4 plus 3, that's going to give me 12 in the table here. So you put in the 2 and carry the 1. And finally, 1 plus 1 is just plain 2. And so this arithmetic is going to be equal to the number 2200 in base 5. All right. So if you were to add things in different bases, you would need your own different arithmetic table here, right? But once you fill in this table as far as the number of digits you have, then you're done, right? You can just use this table to do any addition that you need to do. So let's do another one. This time we're going to do 253 base 6 times 42 base 6. Oh boy, right? This is multiplication, so we need a multiplication table. All right, well, this is base 6, which means we're going to be using the digits 0, 1, 2, 3, 4, and 5. Right, anything after 5, you're going to hit 10, 11, etc. And so in my multiplication table, I'm just doing 0 to 5. 0 times anything is 0, so that makes this first column easy, and the first row easy. And 1 times anything is just that number again. So 1 times 1 is 1, 1 times 2 is 2, all the way down. 2, 3, 4, and 5. So it's not bad so far. 2 times 2 is 4, right? That's fine. 4 is allowed. I have a 4 in my number here. 2 times 3 is 6. We don't have a 6 to use, right? Once we hit 5, we run out of numbers. So after 5, we would have a 10 here. All right, it might actually be useful to go through and do a little counting table for yourself to help you do this multiplication table. So in decimal versus in base 6, we have 1, 2, 3, 4, 5, 6. Okay, so we have 1, 2, 3, 4, 5, then we run out of numbers. So 6 is equivalent to 10, 7 to 11, 8 to 12, 9 to 13, 10 to 14, 11 to 15, 12 to 16. Oh, wait a minute. No such thing as 16. We don't have a 6 to use here. We've run out of digits in the ones place, so now we go up to 20, 21, 22, 23. Okay, and we'll keep going further if we need to. But go back to our table here. 2 times 4 would be our decimal 8, which is equivalent to 12. And 2 times 5 is our decimal 10, which is equivalent to 14 in base 6. Okay, let's fill this in. It's symmetric. Oops, sorry. 10, this would be 12, and this would be 14. 3 times 3 is our 9, which is equivalent to 13 in base 6. 3 times 4 is our 12, which is equivalent to 20 in base 6. 3 times 5 is 15, which is equivalent to 23 in base 6. Symmetric, so I can fill it in like that. 4 times 4 would be 16, which would be 24 in base 6. 4 times 5 is our 20. So what would that be? Oh boy, we'd have to continue our table all the way up to 25. This is a little bit annoying. Well, so maybe just for these last few, I'll just actually do the conversion myself. If I want to know what 20 is equal to, our 20 in decimal in base 6. Right, well, it's 6 plus 6 plus 6 plus 1 plus 1. Right, so it's 3 copies of 6 to the 1 power and 2 copies of 6 to the 0 power. So it'd be 32 base 6. And finally, if I wanted to have 25 in decimal expressed in base 6, well, it'd be 6 plus 6 plus 6 plus 6. That gets us up to 24 plus 1. So we'd have 4 copies of 6 to the 1 plus 1 copy of 6 to the 0. So this is equivalent to 41 base 6. Okay, oof. All right, Now that we filled out our multiplication table, we can actually do this product that we're trying to do. 253 times 42. All right, so 3 times 2 is 10 in base 6. Then 2 times 5, all right, 2 times 5 is 14. But remember, we had to add 1 because we carried the 1. So that'd be like 15. And then 2 times 2, well, that's just 4, plus 1 because we carried the 1, and that's 5. Okay, now we can cross this out, and now we can continue with the 4. So 4 times 3, according to my table here, is 20, and we'd have to carry a 2. 4 times 5 is 32, but we have to add 2 to that, so 34, and carry the 3. Finally, 4 times 2 is just 12, and we add 3 to that, so 13, 14, 15. All right. Now we have to add everything together. 0 plus 0 is 0, 5 plus 0 is 5. 5 plus 4, well, that's 9 for us, but 9 in base 6 is equivalent to 13. 5 plus 1 is 10, but 10 for us is equivalent to, 5 plus 1 is 6, which is equivalent to 10, and then 1 plus 1 is 2. All right, so we end up getting 20350. In base 6. Yikes. So that's a lot of work. Maybe it's easier to just convert it into decimal. I don't know, right? But it's just possible to do these computations staying within your base as long as you understand that addition and multiplication work as they do for us in base 10.